In this video, we will see how to build the speedometer, as seen in the GL Studio Completed Automotive Tutorial project. In its simplest form, GL Studio is a code generator. As such, we will need a compiler to build our projects. Since we are using the Microsoft Windows operating system in this example, we will be using Visual Studio as our compiler. GL Studio includes a Visual Studio application wizard in order to quickly and easily set up a project framework. This wizard generates the source files, the solution, and the project that will serve as a starting point for the design. The starter project is not much to look at, it's just a couple of squares. Double-clicking the GL Studio design file launches the GL Studio Designer, and we can begin to customize the starter project. The designer consists of all the tools, hierarchy controls, 3D layout canvases, and a host of other features and functions to lay out and configure any robust user interface. The drawing canvas functions similar to other popular illustration tools with the ability to arrange content on the canvas, group content, create new content, and it also allows you to work in a true 3D environment. Changes to the project are realized by generating code and rebuilding the project, making for a rapid design, build, and test development cycle. Let's clear the canvas of the wizard-generated content and start by laying out the foundation of the speedometer face using the rectangle tool found in the toolbox. Next, we will apply a texture to the face that contains the angular scale and tick marks for the instrument. GL Studio supports a wide variety of industry-common texture file formats. With the texture loaded into the palette, we will select it and apply it to the rectangle. Every GL Studio object has a set of object properties we can adjust to completely customize the object's appearance. Here we will change the drawing mode of the rectangle to remove the outline. Now let's add the needle. First, we'll toggle the Snap to Grid feature off. Then we'll select the tool and drag out another rectangle. Next, we will add the needle image, which is in a separate image file. So we will add that to the texture palette and apply it to the rectangle. Since the texture image is an atlas of multiple elements, we'll switch to texture placement mode and adjust the texture's size and position on the needle rectangle. With the needle texture wrapping correctly onto the needle rectangle, we're ready to adjust the needle's rotation point. Once we enter object rotation mode, we select the center point of the rotation and drag it to the base of the needle. Zooming in to get the rotation point just right. With the rotation point in place, we can test the needle's range of motion by dragging it along the speedometer's face. Satisfied with its movement, we'll leave it at the 0 mark. At this point, the geometry accurately reflects how we want the interface to look. In the designer, we generate the C++ code for the project and then go back to the compiler to build and run the new design. With the exception of the outline on the needle rectangle, this concludes the first phase of the user interface development, creating geometry. Now it's time to add some behaviors to the speedometer so the needle will move between 0 and 160. Back in the designer, we will do a quick change to the draw mode on the needle to remove the outline, and then we will change the auto-generated names of the GL Studio objects to better represent their function. These names will become the C++ variable names, so they need to comply with proper naming conventions. If the name is non-compliant, the editor will not let you enter it. We will also change the workspace layout to a coding view. This view is useful for maximizing the code editor and code browser canvases. Users have full control over the layout of the panels within GL Studio. This yields a fully customizable working environment for single or multiple screen configurations. For this instrument, we will create two properties. The first property will be a Boolean that we will use for testing, and we will set its initial value to true. In the comment block, we can let folks know that this property is useful for testing functions if we're not connected to a data stream. The second property will obviously be the speed value for driving the motion of the needle. It will be of type float. We'll name it speed, and we'll set its starting value to 0. Every property has a setter and getter method that can be turned on or off to help with memory footprint considerations. They can also be marked as public, private, and protected. Now let's paste in a simple block of code and we'll walk through what's going on. First, we initialize our member variable, and then we have a function to calculate the angular offset of the needle. Using the status window, we can see that the needle moves 240 degrees on its travel of 160 units. This scalar gives us the angular rotation based on the incoming speed value. Now we need to rotate the needle, and I'll delete the pasted text so you can see what the designer does for us while we're editing code. Once we initialize our pointer for the needle, we get a listing of all of the API calls that are available to this object. This is useful for scrubbing through the available function calls. In this case, we want to dynamically rotate the needle at runtime. As we type, we can see the list narrows, showing us a short list of functions and their expected arguments. So we'll select the dynamic rotate function, and we'll specify the angle as the value, and the enumeration for rotation will be about the z-axis. At this point, we are theoretically done. We can build and run the project again, and if we were connected to a data stream, we could watch the needle move to the appropriate speed. But we're not, so let's use that testing flag to drive the needle. This is where the class methods come into play. Initialize is used for code that is called once at startup, and calculate is used for code that is called every frame. This is where we will drive the speed value. So we will do a testing check, which we know is true because we set it that way, and we will make a call to speed. To drive the speed values, we will use a helper function called rampFloat. This function ramps values based on the system time on a sine wave from a minimum value to a maximum value. So let's test the full range of motion of the speedometer and go from 0 to 160. The rampFloat function is in a utility library that comes with GL Studio, so we need to include it in the project. Users can include any of their unique project-specific code this way. Now when we build and run the project, we can see that the speedometer is behaving as expected, with the needle rotating from 0 to 160. Finally, let's create a component. Up until now, this project has used its own windowing mechanism to do the drawing. Since GL Studio is object-oriented, let's build the design as a component so it can be easily incorporated into higher-level designs. Back in the designer, we'll change the generation mode from standalone to component. And in Visual Studio, we will select to build an RSO or reusable software object, and then we will build the DLL. For simplicity's sake, we will use the GL Studio Designer as the windowing element to draw the speedometer component. In a new design, we will select Insert Component from the toolbox and then browse to the folder containing the DLL. As soon as the object loads, we can see that it's behaving as intended, with the speed ramping because the testing flag is on. It is now an asset that we can copy and paste to create multiple instances. Each instance has its own pointer for control. Let's select this instance and look at its property values. We can add a property to track, like the testing flag, and turn it off. Notice this instance stops moving while the other instances keep going. We can continue manipulating properties such as speed, getting the results we expect when we enter in specific property values. Another way to include content into higher level designs is by directly inserting the GL Studio design file. In this case, you get the same effect. But instead of a lightning bolt signifying an RSO, you can click on the eyeglass and it will open the child design. Now in that child design, you can make modifications. In this case, let's add a schematic flow. We'll plot out the schematic path and then use its object properties to load textures for the interconnect texture and the flow. Adjusting them to preview their repeat lengths, speed, and directionality. Saving these changes to the child design immediately influences the parent design that contains the object. No rebuilding of the project is necessary. Using this technique, developers can rapidly iterate through design changes to find an optimal UI construct that will maximize the user experience. You've now seen the basic principles for how to build a user interface element with GL Studio. We encourage you to request a trial version today so you can delve deeper into building advanced, high-fidelity, high-performing 3D user interfaces.